In this video, we're gonna move from extracting simple salts into producing other commodity chemicals out of them. And we're gonna focus specifically on the chloralkali industry. The chloralkali industry is a major source for producing two of the most important chemicals. The first one is chlorine, which is typically used in the production of PVC, paper, and for water treatment purposes. It actually ranks as one of the top 10 chemicals in the United States. The second chemical is sodium hydroxide, which is base that is used in a lot of industries in the production of soap, textiles, chemicals, petroleum refining, and so on. One possible way to produce sodium hydroxide separately is by reacting sodium carbonate with calcium hydroxide to produce sodium hydroxide and precipitate calcium carbonate out. But the major way to produce sodium hydroxide is the chloralkali process. You electrolyze a brine solution to produce both chlorine gas and sodium hydroxide. And this is the overall reaction. It's an oxidation of chloride ions in the solution into chlorine gas and a reduction of water to hydrogen and hydroxide in solution. And that typically occurs at a potential of negative 2.4 volts. The chloralkali process, which is an electrolysis process, can be achieved using three different methods. First one is the mercury cell method. In that cell, you use mercury, liquid mercury, as a cathode during the electrolysis. That eliminates the need for a separator between the positive half cell and the negative half cell. So that's a flow chart that summarizes the process. You start from sodium chloride solution. First, you get rid of different types of impurities through purification steps. And then you take the pure solution, bump it into the electrolysis cell that is going to oxidize chloride ions into chlorine gas, which can then be dried and purified. And in the cathode, you will be producing hydrogen gas and hydroxide ions that can be then filtered to produce around 50% sodium hydroxide solution. The advantage of the mercury cell is that you use mercury cathode and anodes of graphite or modified titanium. The whole advantage is that the liquid mercury cathode eliminates the need of having a separator between the cathode and the anode. And what happens is that at the anode, the oxidation of chloride to chlorine gas is going to take place, and the reduction is going to be actually reduction of sodium ions into sodium amalgam that can be then taken out within the liquid mercury cathode and then redissolved in water to produce the sodium hydroxide solution and hydrogen gas, and separate the mercury again that can be recycled back into the electrolysis cell. And it allows you to produce very pure and high concentration of the sodium hydroxide solution. However, it has a lot of disadvantages because it requires much higher overvoltage to be able to reduce sodium ions, which means much higher energy consumption. Also, it requires a lot of steps for purification, which adds to the costs of the process. And there are also high costs for mercury contamination avoidance steps because of the environmental issues with using mercury. And it also adds some impurities because of the side reactions. For example, at the anode, because we don't have a separator, it's possible that you have some sodium hydroxide in the medium that will partially oxidize chlorine into hypochlorite. So you will have hypochlorite species in the anode compartment, which contaminates the chlorine product. And at the cathode, you could, again, due to the lack of the separator between the two compartments, you could have chlorine gas reduced to chloride, which increases the energy consumption because of these side reactions. The second method for chloralkali production is the diaphragm method, in which use a separator to separate the compartments to allow only flows of specific ions. It functions as a separator that prevents the mixing of hydrogen and chlorine gases, and it also hinders the diffusion of ions, specifically hydroxide ions, from the cathode back to the anode, because the flow rate is going to be the brine solution to the anode to the cathode. It has advantages because it uses much less pure starting materials, and electrodes also can be replaced much closer, which permits a more compact production cell and lowers the electrical resistance and allows using much lower voltages, which decreases the energy consumption. Also, it permits the flow, as we said, of the brine solution from the anode to the cathode, which reduces side reactions and avoids mixing between products and byproducts, especially the formation of sodium hypochlorite, as we described previously. However, it has disadvantages because the sodium hydroxide produced in that solution is much less concentrated compared to the mercury process, and it's also contaminated with chloride ions. The chlorine gas produced from this process also is contaminated with oxygen, and the asbestos separator used requires very high cost to avoid emission because this is a carcinogenic substance and it has a lot of environmental hazards. And these asbestos separators become very easily congested, which hinders the flow and affects the voltage of the cell. So they must be replaced regularly, but this problem can be overcome at least partially by using metal cathodes like titanium coated with rare earth oxides to avoid that congestion problem. The last cell used for chloralkali production is the membrane cell, where the separator between the anode compartment and the cathode compartment in the cell is actually replaced from asbestos to polymeric membranes. This is a flow chart that summarizes the process. You take the sodium chloride solution, purified through several steps that are much more strict than the other processes, and then pump the sodium chloride solution into the electrolysis cell that has polymeric separators instead of the asbestos separator. So the electrolysis will take place. The whole advantage of this method is replacing asbestos with polymeric membranes as separators between cell compartments, avoiding the health hazards of asbestos. And it's also advantageous in the efficiency of membranes of allowing cations only to move through. So it's going to allow cations only to move from the anode to the cathode compartment. So it avoids production of a lot of contaminants because of mixing products. These membranes are very specialized because they have to be water impermeable and ion conducting membranes, and has to be very stable under electrolysis conditions, especially with high salt concentration, high pH jump between the anode and the cathode, and the existence of very strong oxidizing agents like chlorine and hypochlorite. This can be achieved by some special perfluorinated polyethane membranes with some side chains of sulfonic acids or carboxylic acids. However, these are very expensive membranes, which adds to the cost of production. In the membrane cell method, activated titanium is used in the anodes and stainless steel or nickel is used for the cathodes. And the brine used for production has to be much more pure than the other two processes. You have to avoid calcium content, otherwise calcium hydroxide will form and precipitate on the membrane, which will congest it and slow down the flow of the cations. It has Some advantages, as we said, it's going to produce much pure sodium hydroxide because membrane prevents mixing of byproducts or mixing of products to each other. The concentration of the product is much higher than the diaphragm process. It will consume much lower energy, and it does not utilize any of the environmentally problematic substances like mercury or asbestos. However, the sodium hydroxide content much less concentrated compared to the mercury process. For example, the chlorine gas is going to be partially contaminated with oxygen, and it needs very high purity of the starting material, which adds to the cost because you have to take care of a lot of impurities to a very strict limits. And also it has very high costs and limited lifetime membranes in use, which again adds to the cost of the process. The unit operations and different chemical conversions during the chloralkali process includes purifying the brine starting material and then the electrolysis into the products, evaporation and separation of salts, and the final evaporation and finishing of the products, and special purification of the sodium hydroxide product. The brine purification, as we said, has to get rid of any impurities that include calcium, iron, magnesium, salts, which will typically plug the separator diaphragm. That can be achieved by precipitation with sodium hydroxide to remove the hydroxides of these metals. And sometimes additional treatments with phosphates is required, especially for membrane cells, because as we said, it requires much more pure starting materials. Sulfates can be removed by adding barium chloride solution to precipitate sulfates as barium sulfates and separate them. And then you need to preheat the brine solution to reduce the energy requirement during the production. The products undergo evaporation and concentration, and that will have different energy requirements depending on the process. For example, the diaphragm process produces only 11% concentrated sodium hydroxide, while the membrane process produces up to 35%. Mercury process is actually typically within the concentration of 50%. So both the products from the diaphragm and the membrane cell needs to be concentrated to higher concentrations. And after these concentrations, it will crystallize out any salt that can be recycled to the production step again. Sometimes you need to concentrate the product up to 73% to reduce the shipping cost. However, that adds to the shipping and handling problems because it's going to be much more corrosive. Concentrated materials typically have high melting point, which requires steam heated lines and steam heated tanks for shipping. Purification steps of some impurities of the product can be done to remove iron impurities by adding calcium carbonate and filtering the calcium carbonate back to co-crystallize iron impurities out. And sodium chloride and sodium chlorate can be removed by adding ammonia. The other two products from the process are chlorine gas and hydrogen gas. The chlorine gas can be dried and compressed to 240 up to 550 kilopascal. During the compression, heat is removed and gas condenses to liquid chlorine that can be stored in much smaller containers for shipping and handling. Hydrogen can be used in making other compounds, other industries. The reaction between hydrogen and chlorine can be used to produce hydrogen chloride, for example, hydrochloric acid. And it also can be used in a lot of organic industries for hydrogenation steps and for ammonia production, as we will see later on.